So let's try a problem solving example. And for this example, let's suppose you work at Netgear and you are using a MIPS processor to perform motion detection, and we're going to do something similar to what we had in the previous example. We're going to average 3 pixels, adjacent pixels, to detect some movement, and the goal here is to design a hardware that will execute in the least amount of time, be fast as possible, if your software program had steps 1 through 7. This is a very simple example, but it's very practical. It's going to show something useful and help us to work with these terms and define them. So what you're given is a set of parts, and this is what we call a design problem, right? We have a design problem, and we also have an analysis problem. In the design problem, we have to pick parts to meet some design goal. Now, in this particular case, we're given a budget. This is a very typical scenario. They always give us some budget, either monetary budget, or they give us, if you're working on, let's say, an aircraft. I work for IBM, we designed avionics systems. They always give you a weight budget. You can't exceed a certain weight or a certain form factor. So in this case, we're just working with cost, and you can see that some of these parts are $5 parts, and some are $15. I made it a very simple example. But 2 of the parts are processors, and 2 of the parts are memory components. So here we have some memory module. It's a DDR3, and 800 megahertz and 1333. And here's some performance data for each of them, okay? And 10 nanosecond write or 6. So this is a faster part. Or a processor that executes an instruction in 2 nanoseconds versus 1 nanosecond. So if you're on a budget, you can buy this processor for $5. It's going to take 2 nanoseconds per instruction. Or if you want a faster processor, you can buy this for $15. You only have $20 in your budget. The question is, what design do you recommend? The great thing about this problem is the right way to solve this is we have a limited number of parts, we have a limited number of cases. We're going to try and evaluate each particular design alternative. We're going to evaluate each alternative. So, first identify the pair of design choices available. We're building a computer system. Computer system, as we noted, must have a processor and memory. You're going to say, well, what about I/O? Yeah, we need I/O, but in this particular problem, we're only working with the processor and memory. We're not going to design the I/O yet. That's going to be mostly operating systems class. So we need a processor, at least one, and we need a memory, but we're going to have one processor and one memory. We're going to use unicore, okay, no 2 processors yet, no 2 cores yet, just because we're in the first part of the class. So what are our options? We have $20, so we can use this inexpensive processor, only $5, and then the expensive, or the cheap memory. Or we can use the inexpensive, that's 1 and 3, right? We're going to use the inexpensive processor and the expensive memory, which is part number 4, keeps us under $20. You're going to say, well, this didn't spend all the money. Well, the less you spend, the better, but you can't spend more than 20, right? It's a design constraint. If you spend less and you can get the best performance, well, then for sure that's the best choice. You're going to say, well, what do you optimize here? We optimize in performance, but we can't exceed $20. Well, another option is to have the fast processor and the slower memory. What is better? Well, we have to go and compute how long steps 1 through 7, which is the code we have to execute to average 3 values, or 3 pixels in this case, and see how long it executes on each configuration. So let's determine which of these designs is the fastest. So the execution time on the 1-3 pair, which is each instruction taking 2 nanoseconds, each memory access taking, what, in the case 3? 10 nanoseconds is how long? Well, we had 7 instructions in total and 4 memory accesses. You're going to say, well, how'd you get that? Let's go back to the program. It's the previous slide. You can see here that we have 1, 2, 3, 4, 5, 6, 7 instructions in total. Each instruction is going to take the time it takes to execute instruction. Additionally, let me repeat that and point that out, is additional memory access is in addition to instruction execution. Memory access time is in addition to, or adds to, the processor execution time, or instruction execution time. Why is that? Well, to execute the instruction, you have to spend a certain amount of time, and then you have to wait for the memory. They're two separate devices. Each one has execution time. So how many times do we reference memory? Well, read instruction reference memory, that's 1. Another reads 2. Another reads 3. And it writes 4. So we have 4 instructions that reference memory. How long does that take? Well, it depends on how fast of a part you bought. Let's take a look. In the 1-3 case, we have 7 instructions. They take 2 nanoseconds each. I'm going to work in the units of nano here. Yeah, you can write 10 to the minus 9 seconds, but what I like is to work with the native units. Classic example here is if you remember from physics and you work with electron volts instead of using joules, it's just a lot less writing, a lot less math. So I'm going to work with nanoseconds here. So this is 7 instructions at 2 nanoseconds each, and here's 4 memory operations with part number 3 taking 10 nanoseconds each. So that's 40 plus 14 is 54. Well, if I go with the inexpensive processor and inexpensive memory, it's going to take 54 nanoseconds to average those 3 pixels. What's the next choice? Next choice within budget would be the slow processor and fast memory. So this execution time is the same, but memory is faster. So we have 4 memory operations, 6 nanoseconds each. That's 24 plus 14 is 38 nanoseconds. If we have case where we have the fast processor and the slow memory, you can't have fast processor, fast memory exceeds your budget. Can't do it. But if you have the fast processor, slow memory, it took 7 nanoseconds to execute each instruction in total over the whole program, and you had 4 memory operations that took 47. So what do we conclude? We conclude we're going to recommend this MIPS 34K model. Okay, this is just like if you're a car aficionado, this is a BMW 328i, and this is a BMW model 528, or a faster car, bigger engine, whatever. And the same with memory here. So these are 2 different models, and these are what we call the speed specification. All right, this is different models. So you're going to recommend for this customer that maybe it's your boss or whoever was designing this, you have a $20 budget, you're going to recommend this processor and this memory. This is very interesting. To get the fastest running system, you may not want to choose the fastest processor. Why? Well, in the real world, something is always capped. In any real design, there's always some budget. Here, the budget's fixed. So don't spend all the money on the thing that doesn't have the biggest impact. You can see here that memory time is much larger in all the cases. Memory time is much larger than processing time. You're going to say, well, I just made up this example to make these numbers work. But in the real world, memory is about 10 times or more slower than processor. And the point is that you need to know these types of relative speeds for the actual system that you're building to make good design decisions. So you can even use this, suppose you're buying a laptop, and this is a little bit trapped, but sometimes Dell wants to make money, and that's their job, right? They're a business, and they're going to sell you a 3 gigahertz or a 3.4 gigahertz, and they're going to charge you $500 more. Well, you might be better off spending that $500 to expand the memory of your machine versus, or especially cache. On-chip cache can make a processor run much, much faster. That would be my typical recommendation. Okay, but how do you know the actual values? You have to look at the actual code being executed. It's a difficult problem. You can run benchmarks. That's another module. We'll show you how to do that. But this particular example, you can see we can apply the concept or abstraction of processor and memory to choose some real parts and execute a program which has some assembly language statements that really does something that a C program would do. This is a very simple example, but it fits on one slide. I try to make my examples fit on one slide. Okay. So here you can see this is what I was looking for in the previous slide. The recap physical view. Each bus is a bundle of wires. Each wire is what we call a wire trace on a circuit board, and we have 1 wire per bit. Why? Because we're electrical engineers, we use voltage levels. A wire can only have 1 voltage at a time. That's from physics. Okay? Electrons, I say a wire can have voltage. wire can provide a potential difference between 2 points in a circuit, which is only one potential difference at any given instant. You can change that. That's a transient response over time, but you can only have one voltage value at a time. So let's do a calculation of address bus and data bus. We've been mentioning these, see a few examples. Let's make it more concrete. Computer system has a single core 32-bit processor and 8 gigabytes of byte addressable memory. So the 32-bit processor is referring to the data bus, which is the first question. So it's the 32-bit processor, means 32-bit word width, means that there's 32 wires on the data bus between processor and memory. What am I talking about? This data bus has 32 wires. I can put a little tick mark. You put a tick mark here and write the number 32. That is the number of wires on that bus. A bus is a bundle of wires. What about the memory capacity? Memory capacity is given here as 8 gigabytes. 8 gigabytes of byte addressable memory. You're going to say, well, what do you mean byte addressable? In this course, as in the real world, every memory chip is always byte addressable. Means even though we can transfer a word at a time, you can get down to the resolution of a byte. We'll explain it later. But the point is, if you have 8 gigabytes and it's byte addressable, you have to have enough address bits, you see, on your address bus to specify any of 8 giga locations in this memory. I draw this way. I call it the depth of the memory and the width of the memory. We're going to come back to this later, but we just define it now. So a memory is a linear array of storage cells. Address is written outside the memory. It's not actually stored there, but the address goes from address 0 up to the last address, which is all ones if it's binary. I'll even write a number as a binary number here, base 2. And inside the memory are cells, which are values that are being stored. So I call this the depth of the memory, or I don't call this, everybody does. And this is the so-called width of the memory. In bits, the units are bits, the units are bits. So the width of this is how many bits are stored here, how many zeros and ones are stored for each cell. This is a cell. This is another cell. It's a cell inside of a structure. That's the depth of the memory, and this is the width of the memory. So in this particular problem, they're asking you to say, find for me the number of wires on the address bus. Well, I have to access 8 gigabytes, 1 byte at a time. That means I need enough wires to get the corresponding number of bits. Well, how many bits is that? Remember, we had kilo, mega, giga. So we had 2 to the 10, 10 for kilo, 20 for mega, and 30 for giga, 2 to the 30. And what's 8? 8 is 2 to the 3. So 3 plus 30 is 33. You need at least, without me, we're going to see the solution in a minute, without me, I can use the exponent rule, which we showed you last time. I know I need at least 33 wires on that address bus. Okay, 33 wires at a minimum. Let's look at the math. 8 gigabytes of byte addressable memory means enough wires to index any distinct byte within that memory depth. So I have 8 is 2 to the 3 and giga is 2 to the 30. It's byte addressable means there's 2 to 33 bytes addressable range. Since each address wire doubles the addressing range, because it's binary number, I add a binary digit, I double the range. The number of bits required is ceiling log base 2 of the addressable range. If I stay in binary, which is the easy way, it's the natural units, you're working with powers of 2. Just memorize your powers of 2. I know that that is 33. In other words, if you take, we can do it here. Let's take with a calculator and go to scientific mode. And we say 2 raised to the 33rd power. That is 8 giga as a decimal number. You're going to say, well, why is it not 8 billion? Well, remember, this is 2 to the 33, and 2 to the 10 is 1024, not 1,000. So if I take the log of that, it's 33. Log base 2. Log, right? Log could be base 10. Log could be base 2. When we work with binary, we use log base 2. So log base 2 of that number is 33. I need 33 digits to specify 2 to the 33 distinct values. That's a lot of values. But that's only 8 giga. Forget tera. That's just 8 giga. So we know there's at least 33 wires on the address bus. What am I asking you to envision? Okay, remember, draw the diagram, figure out how it works. There's 33 wires between that processor and that memory if the depth of that memory is 8 giga. So what we're seeing here is we're starting to design real hardware, even in the second week here, using this process of abstraction. So let's break here, and then we're going to go to computer system elements is the next module. So here is a very common abstraction of computer. We continue here with computer subsystems, or the so-called 5 basic elements of a computer system. It's probably the most widely used computer abstraction, and everybody speaks these terms. You should have a very good handle. We're going to refer to them throughout the course. So here we can see a block diagram. Block diagram is what I call the clear box view. Okay, clear box view, we see inside the box here, and inside the computer system. This is computer system boundary. Okay, what's outside the computer system? Well, maybe it's the internet, connecting or intranet that your computers are connected to, and there's some link to get there, but we can see memory central in this design between the processor and the I/O devices. So we see the 5 primary elements. Memory stores bits, processor crunches bits. It uses 2 separate control circuit and a data path circuit that work together. These are the actual bits that are flowing that get changed. That's the data or data path. And the state machine that increments the program counter, we saw the program counter getting incremented to the next instruction. The actual logic that makes decisions, like we saw the jump if, that helps us make a control statement to make the machine intelligent or do something useful. That's part of the control path. Input and output devices either get data into memory or remove data from memory. In this class, we don't talk about networks. That's a separate class. We typically work with inside what we call the computer system boundary. And main memory, in our case, refers to primary storage like DDR, the 8 gigabytes rather than the cache. We'll find out later cache is actually inside the processor, a small amount of memory that's put there to make the processor faster. We'll explain why. As I mentioned before, processor CPU are synonymous, and some processor chips also contain small amounts of memory, which we'll explain. The link depicted here is some type of either bus structure or packet switching structure. There's things nowadays called network on a chip, or NOC. We can actually transfer data between these elements as if it's a packet switch network. What is that good for? If you have a lot of cores. Right now we're only going with 1 core. When we're going with 1 core, we typically use some buses here as link elements. We'll explain. So let's look at these components from a physical view. Physical view here, we're given this as a computer gaming board. It's a pretty new one, and powerful AMD FX processor. And we can see the different elements here. So let's see what we learned in the previous. Can we identify these different components on this motherboard? And here you can see these are components we want to identify. So processor, memory, and input-output, they're color-coded. So what about the processor on this board? So the processor obviously goes into the socket. So if you're a gamer or you want to design systems, a nice way to get started is board-level design. Build your own system. You start here with a bare motherboard, and you can populate this with the components. So here we have the socket for the processor, and a lot of times these are ball grid arrays. They're actually hundreds of pins, maybe up to 1,000 pins on these processors, and they go into the socket. and it's connected from the socket. The address bus and data bus are actually connecting to these, see these module slots here? So this is where the memory goes. So let's identify these components. So processor, you can see the AMD processor here. I've just circled it the same color, yellow. And these are expansion slots, but here's memory slots. Okay, memory slots for DDR. What about input and output devices? Input and output devices, you see Ethernet, back I/O here. So we can see different types of input and output devices. Here's for hard drive, SATA. And we can see these different components present on the motherboard. So the point is, if we actually looked at this, you'd see traces between the processor and memory, or these I/O devices and various elements, either memory or processor has some control lines. And we'll look at these in more detail. These are color-coded sometimes. There's red slots and black slots. Ones that are closer to the processor tend to be faster. We'll talk about this. It's actually physical constraints of distance that can affect speed because we're working at gigahertz range. And what about this? This is a type of link. Okay. Here we see, instead of the physical view at a board level, we see a processor chip. And this is a photomicrograph of a processor. Here we're seeing, anytime we see regular structures, as I mentioned, these are typically memory. Cache is a form of memory. But if you look inside the floating point unit or the instruction, decode, and execute units, they're a lot more random, a little bit less regular than the memory arrays are. But the processor that we see here with 4 cores, we're looking at a single core here, has the same type of components we see on the motherboard. It has memory. It has processing units. Okay. And it has some input and output, which are on the edge of the chip. So we see these 5 basic components. Okay, there's control path, which is the here a fetch and decode unit. Execution is part of the data path, because that's where the bits are actually get crunched in the execution unit. And we see the memory component here, which is cache. So we see practically on all computer systems, whether they're board level or they're chip level design, we see the 5 basic elements of control, data path, memory, input, and output. You can think of them as your 5 basic food groups. You will have them in every computer system in one form or another. So to understand what those components are, how they function, we can look at these levels of abstraction and the hardware-software interface we call the instruction set. A lot of these constraints interact with one another, so this concept of computer architecture, we have constraints of cost and power. We already saw a very simple example. But programming languages may influence which computer architecture choice you want to have, the technology that's available, which operating system you're using, legacy concerns. You want to be backwards compatible with other devices that you already have built or you're going to buy from other vendors, or software. Sometimes it's cheaper to maintain compatibility just because of the investment in the software that you have. So the idea of a computer architect is just like a building architect in civil engineering that needs to design a structure to meet some balance between goals and different constraints that are present, like budget. We have to trade these off. That's a computer architect's job, right? So we're going to learn design techniques. We've already seen a couple design problems. Measurement, which are our metrics, and how to evaluate these and trade them off. So here we see a nice abstraction. I wrote this in pen myself, but now we see a little bit more detail. I assembled this from a couple different slides, but this shows our abstraction increasing as we go up. So we say that application level programs, high level programs, are most abstract. And Boolean gates, physical design, actually there's transistors below this, are the least abstract, okay? But we can see the different layers, and we go from application, assembly, system, software, machine code, register level structures, okay, like adders, multipliers, counters. So we're going to use Boolean gates in this class and design some of these structures and then use them to implement different instructions as machine code. So your question is, what's the difference between machine code and a program that a programmer may write? Well, we saw a level of abstraction. We had a C program that had average A plus B plus C, but that had many machine instructions. What we looked at were what we call human readable instructions, or mnemonics. Mnemonic is something that helps us remember. It's a memory aid. And this LW was load word. Remember load word I said was a read instruction? And store word, you're going to see these in the lab this week. But what the machine actually executes is bits. Why? Because instructions are stored as bits. So how do we go from here to here? We have some mapping, we have some system software. Either we translate this using an assembler, or we can interpret this, but we have some routines here that help us connect to input and output devices. We call that system software. We're going to talk about mainly these levels here in this class. So how do these levels interact? I think I've talked a lot about these, but we haven't talked about is how we actually make this translation from one level to another. To run an application program, you have to get to machine language. Why? Because the hardware only executes machine code. Let me say that again. There's no computer system anywhere on the planet that can understand a for statement. It has to be decoded to a sequence of bits. So we use some system software to do that. Assemblers translate these high-level instructions to machine code. So in a number of steps. So actually they translate assembly language to machine code, and compilers translate high-level programs to assembly. So the actual flow looks like this. We start with the high-level language. I should write this down. What is a high-level language? Well, things that we use every day, for example, C, C++, okay, maybe Java, okay, are all high-level languages. High-level languages are very abstract from a hardware point of view. There's something that the programmer can understand in terms of an algorithm. He can write an algorithm with a high-level language. What's the problem with a high-level language? You can't run it. It has to be converted to bits. We do that in steps. We convert a high-level language into assembly language using a compiler. Let me say that again. A compiler's job is to convert high-level language statements to assembly language. But assembly language is still human readable. We have to convert assembly to sequence of bits. Okay. Now, your compiler makes this translation, assembler makes this translation. A lot of times we run a compiler, you say, well, I was able to run my program directly, and I got an exe file, which is a sequence of bits. I had no assembler. Actually, you can run this directly, and the assembly process is executed automatically. And we don't see that. But if you have, let's say you're running in GNU C, right? You can use the switch to save the assembly output and so forth. Or you can use an assembler directly, is what we do in this class, so we can understand the instructions. Let's take an example. So here's the C program. What's this program doing? It's interchanging two variables. Here we have the value v sub k, and we want to do what with it? We want to interchange that, okay, with another value, and the integer k is the index that we want to interchange. So here we want to say temp stores the value of v sub k takes the value of v sub k plus 1, and then v plus 1 takes the value of temp. So what we've done is we've interchanged v sub k array value and v sub k plus 1 value. Well, the programmer may write this sequence of statements, we use the word statement, statements in C. This has 3 statements. The compiler will translate this. It's usually a one-to-many mapping, as we already saw. You may have one statement in C, may map to many assembly language statements. So let's take a look. Here is assembly language for MIPS code. We said load word was a MIPS type of read, and store word, SW. These are mnemonics. They're helping us remember this by a sequence of characters. So store word is actually writing to memory, and here are operands. And this is how assembly language is laid out. You'll see in the lab you have an instruction followed by some operand, This could be output operand for MIPS and a set of input operands, and we'll discuss this. But the machine still cannot execute this sequence of assembly language. This is for the human to read. We have to convert this to a sequence of bits. So we have 7 instructions here. The assembler will convert these to binary digits, and we get machine code. So what actually gets executed to perform this interchange of two arrayed values that are stored to adjacent arrayed values is actually this sequence of bits. The sequence of bits turns on and off the corresponding circuits. Now this could be data that we're going to crunch, and this could be the instruction that we need to execute. We're going to show you that in coding in Module 5. So we'll actually show how instructions are encoded, how to build a processor, and how to optimize it for this given encoding. So let's take a look at some of these steps here. These are actually hardware instructions. You have 7 of them. Now the interesting thing is a one-to-one mapping. So usually between assembly language, I should say usually, I say always, between assembly language and machine code is a one-to-one mapping. The only exception is if this is a pseudo instruction, which is a pseudo instruction may represent more than one binary machine code instruction. But we call these assembly language instructions. These are machine code instructions. These are high-level instructions. We have to have some idea what these are in order to design circuits to execute them and then optimize them. Here's another graphic showing this process of translation and this concept of semantic gap. Semantic gap is the difference between what the programmer wants to execute and what hardware can do. That's semantic gap. So we bridge the semantic gap by a series of translation steps. So semantic gap between high-level language and assembly language. You can read here some of the advantages of high-level that I've already mentioned. This is the way programmers think. It's very good for productivity because we can work with abstract concepts like arrays and indices, and we don't get into the lower-level details of bits and bytes. But assembly language also has a purpose. If we want to have deterministic code that we know exactly how long it takes to execute, let's say it's a kernel of an operating system, it's something that's very critical. It's executed millions of times per second or millions of times per hour or per day. Or if it's an application that you have to bound the execution time, we can look at the assembly language and have that be very, very precise, very concise and exact. For our purposes, it also shows us how the bits get crunched, and that's going to help us design circuits. So let's look at CPU instructions as more detailed or less abstract views of high-level language. We call these statements in high-level language, each line of code, and instructions are a statement of assembly language. When assembly language is translated to binary, as I mentioned, it's called machine code. And again, any C program that you've ever written and compiled, a Windows program browser, if you go to program files, C:program files on your Windows machine, there are a set of binary files storing all the instructions to execute that program as a sequence of bits. So that's the job of the compiler to make the translation to assembly and assembler to make the translation to binary or machine code. So the interesting thing as engineers, people usually hire us to perform trade-offs, is there's what I call a space versus time trade-off. Well, a lot of authors call that. It's a very fundamental concept. We can use more instructions and have maybe a different time trade-off, which means how long it takes to execute. So this is a number of physical resources, including chip area and even energy, versus execution time. Okay, so let's take a look at this next example as compiler optimizations. Why am I taking the time to give this example? Because it's going to show what a compiler does and some trade-offs between space and time. Optimization levels is something you may encounter on a real machine. Also, it's going to help us practice powers of 2 and bits and bytes. So let's take a look. This is a very realistic scenario. You work at Microsoft, and that fits on one slide. You work at Microsoft in hardware platform support. What does that mean? Well, you happen to get a job in sales there, and you're at a trade show, and you're talking about this new Visual Studio release, and it's going to translate C code from 64-bit machine code. Output is your objective from high-level language. Transferred C++ gets translated into machine code using assembly language and assembler in the middle. Here we have 64 bits per instruction, and we have different optimization levels. Optimization levels vary the mapping. So here we had a mapping from 3 instructions, or we call statements, of high-level code to 7 instructions. But maybe there's some more powerful instructions. We end up with fewer instructions, but they may take longer to execute. That's a space versus time trade-off. So let's look at that in terms of these optimization levels. Most compilers support different optimization levels. And if you don't use any optimization, it's what's so-called baseline translation. And what we're seeing here is different optimization levels and what they have for what we call the unit program. The unit program takes 1 second to execute, and it took 1K bytes of machine code space in memory. So the client's program, however, has 2048 machine language instructions that executes in 100 milliseconds. So you're at the trade show, and you have this data sheet for the system that you're selling, but the potential client is interested to know what's the performance improvement if it's going to use the different compiler optimizations in the new release. So you're making translations from high-level C++ code to machine code. But the translation that occurs could cause the code to run faster, slower, take more memory space, or less memory space. Why do you care about this? Well, suppose it's a client that has that wants to buy their Oracle, and they want to buy 10,000 seats of this program. Well, you'd like to give them a concrete answer. So how do you go about this? Well, first we're going to determine the size of the client's code in bytes. So we said here that there are 2 times 2 to the 10. Where did I get that? Well, 2 to the 10 is 1024. So we see 2048 is a power of 2. It's 2 times 2 to the 10. It's 2K. In this case, each instruction has how many bits? Well, it's a 64-bit machine. So each instruction has 64 bits. How many bits per byte? Well, there's always 8 bits per byte. And then we're going to do, this is in units of instructions, right? But we have to get to bytes. Why do we have to get to bytes? Because this column of the table is in units of bytes. So how many bytes do we have? We have 2 to the 1 times 2 to the 10 is 2 to the 11. This is 2 to the 8, sorry, it's 2 to 6. 2 to the 6, and then we have 8 bits. So we're going to divide by 8. 8 is 2 to the 3. So we have 2 to the 1 is 11, plus 6, 2 to the 6, 64, and then minus 3. And we end up with 11 plus 6 is 17, minus 3 is 14. And what is that? 2 to the 14 is 2 to the 4 times 2 to the 10. 2 to the 4 is 16. 2 to the 4 is 16 times 2 to the 10 is kilo. 16 kilobytes. So the client's code is 16 times larger than the reference code. All right. Next, consider an optimization 00. We start with that. That was what the client currently runs. So without optimization, the client's 100 millisecond execution time is 1/10 that of the, excuse me, 1/10 of that is 100 milliseconds. Great question. How many milliseconds in a second is 1,000, right? 1 second equals 1,000 milliseconds. Okay. So 1/10 of a second is 100 milliseconds. So it's a factor of 10. Why am I using optimization 0? Because it says here this is without optimization, executes in 1/10 of a second. Get used to these units. Okay, 100 milliseconds should mean something to you in human terms. Just like when I said it's 95 degrees outside, that should mean something to you. 100 milliseconds should be, in human terms, that's 1/10 of a second. So for time performance, we're going to scale down the values by a factor of 10. However, these are independent. This is time and this is space. So the factor is 1/10 for the time, but what about space? Is actually 16 times as much. So for O1, the client sees anticipated of what? So if you went from 1 second to 1.2 seconds for the unit program, here we're going to go from 100 milliseconds to 120 milliseconds. What about size? Size went from 1K to 512. What is that? 1K is 1024. This is 512 is half. So it's actually 8 kilobytes in size. Under O2 optimization, what is anticipated? Well, O2 is for maximum speed. O1 is for minimum size. So what's the trade-off? Well, you make the size smaller. Okay, it may take longer to run. If you make the size larger, it may take less to run. That sounds very strange, and I'll explain why. There's something called loop unrolling. But here we see the same calculation that it was 60 milliseconds, and the size goes from 1K to 1 meg. What's that factor? That's a factor of 1024. That's huge. So this is really, sometimes these are highly nonlinear, right? To basically cut the execution time in half, roughly, right? From 1 second down to 0.6 of a second, you had to actually incur a space cost of a factor of 1024. That's huge. So we'll explain about this in a minute. So here's this, everything is recapping from the previous slide. Okay. So, what statements can you elaborate to the client about using Microsoft's compiler technology? Well, you're able to do these types of scaling in your head or with a small calculator. That's fine, but you have to speak something in words. You want to sell this product, you want to get the 10,000 seat installation, and then you get a vacation, I don't know, to Fiji or something nice. So, what do you have to, you can't just show the guy the calculator, you have to explain in words. So what I would say, we can make this very simple so we can see what we're thinking about how this works and what we've concluded. What's our conclusion? Modifying the C++, this can be a quiz question. Modifying the translation from C++ to machine code, that was the translation, using optimization to modify it, can reduce the number of instructions from 2048 to 1024. True or false? Well, what are we doing here? We're cutting in half. Yeah, we see that happening here. You're going to use O1 to do that. Use O1. Suppose a client wants to cut the size of his code in half. Suggest O1. It will achieve it. Now, if the client wants to cut the size of the code by 20, cut it in quarters, right? Cut it by a factor of 4 to be 25% of the original value. This is not going to get the job done. So don't tell them that because they might be disappointed later. Next question. The optimization choices allow the program to execute faster by making the code size smaller. True or false? When we execute with the O2 optimization for maximum speed, it does execute faster, but the code gets larger, not smaller. Well, that seems counterintuitive, but there's something very important that's occurring here. O2 eliminates the overhead by reducing the testing of loop counters. So sometimes you can have compact code and use loops. But when we have loops, we have to increment the loop counter, the index, and then we have to test it and branch back up if the loop still has to execute. That takes more time than just making the center of the loop, we call the body of the loop, replicated multiple times. So here's our two choices. So one choice is to have a loop for I equals, and then we have this so-called body of code. And then we're going through this, I don't know, from 1 to the, what's a large number here, 10,000. I can unroll this. And in the unrolled version, this is the so-called rolled loop. Okay. We execute this as many times, 10,000 times. What I'm going to do here is actually in space have 10,000 instances of that loop. And guess what? Even though this code is larger space, greater space requirement, the time requirement is less. Why? I don't have to check, I don't have to increment this I, this I plus plus here. I don't have to increment that and I don't have to test it to see if it's a loop limit. I can just go what I call here straight line code. Straight line code executes the fastest. So even though the program is longer in terms of size, it's faster in terms of time. So these are time versus space trade-offs. This is part of abstraction, moving between high-level languages and machine code. You're going to say, well, why do I care about this? Because there's a lot of flexibility that can allow optimizations that affects the real hardware. These are trade-offs that people may ask you to make between time and space by abstracting the execution into different formats and different levels of abstraction between machine code that have different times and space trade-offs. So how do we work with these in the laboratory? In your lab, you'll see that here you will install the MARS, which is a MIPS assembler and simulator tool. And this tool, you can see here, machine code instructions. And here's comments, which each one of these do. These are put in by a human. These are human readable. And when you click here to run this, it will actually assemble this and make the machine code. You can see some binary values. This will be explained in the lab. But these are the registers. Registers are storage elements inside the CPU chip. In the MIPS machine, each register is 32 bits. These are hex. Okay, so I want to get this very clear right now. Anytime we have 0x, 1, 2, let's say, this number x here is 0x actually. This 0x that precedes any number means that the value is in hexadecimal. Hexadecimal means 16. Decimal means 10. What is hex? If you have a hexagon, how many sides? 6. 6 plus 10 is 16. So hexadecimal is a base 16. One way to write that, I can write 12 HEX. Or a lot of compilers started from C. 0x means hex. So 0x12 is hex. What is that number in decimal? Great question. Well, it's 2 plus 2 times 6. This is 16 to the zeros place, right? What is this place? 16 to the 1 place. So you have 2 times 16 to the 0. 16 to the 0 is 1. So you have 2 1s plus what? 116. 16 to the 1, 16 is 18. Okay. So here you can see hexadecimal values are all initialized to 0 right now. That's fine. But there's different registers. We'll explain what these are. And here's different instructions corresponding to the instruction set of the MIPS processor. This is the middle layer between software above and hardware below. So we can see that middle layer. We sometimes even say that software runs on hardware. You can see here this hardware is holding up the instruction set, okay, and the software is running on top of it. It's helpful to learn assembly language to see how hardware operates, how software uses hardware to design instructions. And then you can also use this if you want to design some optimizations, let's say for operating system kernel, device driver. You're going to do that in embedded systems. You're probably going to do it in senior design. And this is a way to understand the operations in terms of the hardware, to debug hardware, build interfaces. We need to know how bits and bytes are transferred and how instructions are executed. You do have accessibility to the system hardware when you work at this level. When you work in C, it's an abstraction. You don't actually control the hardware. It gets translated to assembly and then machine code for you. But here we're actually going to work with the real instructions that control the real hardware. And you can trade off time and space, as we saw in the previous example with compiler optimizations, and tune your performance for the customer. So this leads to the concept of instruction set architecture. We only have a few slides left. So instruction set architecture, you should know this concept. It's also called processor architecture. This is the interface between hardware and software. And what is that? That is the set of instructions for that machine. For MIPS, we can see some instructions. Load address, load word, load immediate, add, store word. These are the instructions of the machine. That is the so-called instruction set architecture. So how we architected the machine into instruction abstraction. It's interesting. There's a lot of trade-offs. Intel's instruction set's completely different from ARM's. ARM's and MIPS are almost the same. And it depends. Embedded systems tend to have very simple instruction, relatively simple instruction sets, a few number of instructions, limited number of registers. Complex processors have very complex instructions. It makes it very difficult to design and understand. For example, Intel has, I think, 300 and some instructions, 350. They're always adding some. And they're variable formats. Some are 8-bit, some are 16-bit. They're all over the place. They can go up to 64. That's fine. But that defines the instruction set architecture. The ones we like to work with for our first course is something that has a fixed instruction encoding. They're always 32 bits in exactly the same order, in the same format, so we can understand it. There's something else called ABI. ABI is our application binary interface, and that is the system software that's doing the translation to go from high level to the instruction set. Okay. We'll cover that in a later module. So here is our final use of these components of abstraction. Another way to look at these is in terms of their characteristics. We have single user systems. These typically tend to have rich interface, point and touch, or graphics displays, good sound and audio. Multi-user systems, today they're servers. They used to be mainframes. Mainframe got to be too expensive. It becomes cheaper just to put PCs in a rack. That's great because they can be switched out for reliability. They're inexpensive. They're easy to upgrade. And we'll talk more about parallel processing and how to use multiple cores or multiple PCs together as a less expensive cost option. Supercomputers are the next level up in the echelon of complexity. Supercomputing is the data crunching side, and data warehouse is the data storage side. These are highly specialized, really have very minimal front end, but they're all about crunching bits. And then we have embedded systems. They have some elements, embedded systems have some elements of all of the other three components. But one thing sets them apart. They are linked to a predetermined application. They're typically optimized to do one particular job. Maybe some type of controller for a motor interface. They're typically linked to very closely to the application, where these are general purpose machines. The interesting thing about this, for your generation and employment even a few years from now, is Internet of Things, a big area of hiring, is all in the embedded system space. Well, to understand embedded systems, you have to know what a processor does and then how to interface to it, the bit encoding and so forth, which we'll cover. But Internet of Things is really designing minimal footprint, very energy efficient, very inexpensive parts. Here's one. This is Intel Edison. Actually has a dual core Intel processor, is basically a Pentium processor, on an SD card size form factor. That's amazing. So this is where embedded systems are headed, and a lot of these can be so energy efficient. I'll show you in a few slides in another module. It can run from a solar cell and never need a battery ever, and still run Linux or run Windows even in very limited memory space. But this is Internet of Things. So here's our last slide showing a typical handheld device and all of our 5 components working together. We can see here processor and processor characteristics. What do we care about? The number of cores. Well, with 1 core so far in the class. Processor speed. So memory storage, SIM, which is non-volatile. Here's RAM, which is 2 gigabytes of DDR, which is volatile memory. It requires energy to store the bits, but it tends to be fast. Non-volatile memory tends to be slow. Why? Because we have to use a capacitor. It takes a long time to charge relative to switching a transistor on and off. Or memory that is magnetic, that is non-volatile. You take different designs, but it typically can take a longer time to write that value to a magnetic device, especially if it's an electromechanical device like a disk. but they are non-volatile. We have rich interface, input devices, right? We had input was one of our 5 components. Output devices, multimedia, battery, Wi-Fi, everything integrated in one package. It's amazing. We'll talk about this in device technology, just how amazing this really is, and in a historical perspective, even 10 years ago, you could never have this level of integration and this functionality for such an inexpensive cost. So here's our summary for this module. We have introduced the concept of hierarchical abstraction. It's a very important concept throughout engineering. We use it in computing because computing spans from transistors, a single transistor for a few gates, or 2 transistors for an inverter, up to billions for a processor, and we have to abstract away the detail, and we look at this functionally. We look at the interaction between processor and memory, which is our primary abstraction. In the simplest dichotomy, we execute instructions here, and we store data here. We move them back and forth. There are ways to combine these, but that's a graduate level course. We'll get to that in the future if you stay in the program. So the idea of memory stores values. There's billions of them, gigabytes capacity. Millions would be megabytes. But we have address and data. Address is depth of the memory. Data is width. And compiler and assembler are the binary translating software, or we call middleware, programs that help us to make these translations. And we'll cover these in more detail in a later module for you. But these are important for job interviews, especially because these mappings come up a lot, so you can understand some of these. As we go through the class, we're going to introduce them in this module, and we're going to keep talking about making a mapping between something that's human readable and machine code, whether it's instructions going from assembly to machine code, or data, that if it's a letter, we'll talk about ASCII codes to encode data and so forth. Everything that we saw in this module, we're going to cover in more detail in later modules. Thank you, everyone, and remember, this week's lab will install Mars and get started with some simple example moving data back and forth between processor and memory.